All right, on page, I think we finished the first two at the bottom, is that right? Okay, so we're looking at these improper integrals. Okay, they kind of involve a bound that has infinity. And so we have to be a little tricky or careful on when we actually think about plugging in that bound, how we analyze it. So I think yesterday the first two, in order to do by hand, we did by parts as our technique. Let's go ahead and try letter C. What do you guys feel like doing for that one? We did our mega integration worksheet. You guys said you felt a little bit more comfortable integrating after that. What do you feel like doing?
I feel like...
Besides crying or quitting or... I know.
I feel like we should try that.
Partial fractions? Okay, so how does partial fractions work? This is Maddie's favorite, I think I remember. Yeah. Okay, you want to take control? Go ahead.
Yeah.
Okay.
Factor the bottom.
Factor the bottom.
This is the one thing I know how to do.
All right, two numbers that multiply to 3 add to 4. 3 and 1. Okay.
And then we would multiply a by x plus 1.
Okay. You got it. Yeah, you're skipping a bunch of steps, but you have the right idea. So with those two factors, we're going to split up the original fraction or integral into the partial fractions. So we'll use kind of temporary numerators because we're eventually going to figure out what those values are. So Maddie went on to say we're going to do a little multiplication here. We're going to have a times the x plus 1 factor and then b times the x plus 3 factor as if you were getting a common denominator. You want to keep going, Maddie?
Okay. And then you set that equal to 2.
To 2? Yep, the original numerator. Looks good.
And then you plug in a number that would make b 0.
Okay,
So
so
that'd be negative 3.
all right. So if we were to plug in negative 3 for all the x's, we'd have 2 equals negative 2a, and then the b would go away. So it looks like a is negative 1.
And then you plug in negative 1.
Okay. Because that'll get rid of the a, and we can solve for b. Looks like we get 1. So if you wanted to, you could fill in your temporary numerators now. This would be a negative 1 up top and a positive 1. So if you were to, let's say, integrate, what would we look like if we work backwards?
X plus 1 over x plus 3.
All right, natural log of x plus 1. You have a positive 1 coefficient. And then you said minus natural log of x plus 3. She used the minus 1 coefficient in front of that one. You could have it reordered, okay, because I know we wrote this one first, that one second. You could have it reordered. And our bounds are from infinity to 0. All right, now since we're dealing with natural logs, it might be in our best interest to see if we can use a property of logs to go a little bit further, because if you really thought about plugging in infinity here, we're trying to perhaps, if we can make it a fraction, that would be in our best interest so we can utilize the growth rates to help us figure out what's growing faster than the other one. So is there a property of logs that we can use to somehow combine these two individual ones together? Yeah.
Because you're subtracting logs with the same base, you can make it.
There we go. We're subtracting the same log, and they have the same kind of coefficient out front. That's important. If this was a 2 and that was a 1, you couldn't use that property. It have to be the same log and the same coefficient. So what would it look like, Eric? You said natural log of
X plus 1 over x plus 3.
over x plus 3. Good. All right. So let's go ahead and think about our bounds. If you were to plug in infinity for those x's, Okay, think about your growth rates. Is the top growing faster? Is the bottom growing faster? Or are they technically growing at the same rate? How do you know? They both have an x to the first power. If you think about it, if you plug in infinity, does adding 1 or subtracting 3 really affect that value at all? If you think about infinity. So whatever numbers are left out here, they're kind of insignificant. You're really concerned with the rate or the variable that is affecting that motion towards infinity. So since they have the same rate, what do we know that, or what value do we know we're approaching? How'd you get 1? It's the ratio of the coefficients. So if you thought about plugging in infinity, they have the same growth rate, so we are approaching the ratio of those coefficients. So really, we're left with the natural log of 1. That's what we get when we think about plugging in infinity. So now we have to subtract what we get when we plug in the lower bound, which would be 0. So that would be the natural log of 1/3. What's the natural log of 1? It's 0. Good. Okay, so I know they're hard, right? Do we remember the natural logs, the 3 that we gotta know? Natural log of 0, natural log of 1, natural log of e. Those are the ones you gotta know without a calculator. Natural log of 0? Undefined, doesn't exist. Natural log of 1? 0. Natural log of e? 1. Yeah. Good. Good, good, good. All right. We're going to continue with some more examples today of these improper integrals, just looking at bounds that have some type of an infinity in them, maybe 2 infinities, like the next one we're going to check out. 2 infinities and beyond, okay? All right. The moment of truth here. Let's think about going backwards, integration techniques. You can think about this as a 1 up top, perhaps. Go ahead, Eric.
Should we split it up into separate integrals?
Into 2 what?
Separate integrals?
Like what? What would they look like?
Like negative infinity, 0, and 0 to infinity.
Why do you want to break it up at 0?
It seems like a nice little round number.
You could do that, okay.
Just seems like a nice.
How about, you don't have to write this down just yet. We'll think about it. No, that doesn't mean it's wrong. I just want you to think about it. It's not wrong.
Oh, well,
Okay, then we'll break it up to 1 then. Should we do that? Because that's what we do for everything else.
You could do this. You could break it up at 0. You could break it up at 1. You could break it up at negative 100 if you wanted to. I mean, as long as that's a property of integrals. You can break it up at any point as long as you're adding them together. So 0 is fine. But by breaking it up, you're now working with 2 integrals that are basically the same instead of 1. Which is fine. Where do you want to go from there? That's the question. So you can break it up, mathematically possible.
We evaluate each integral separately.
We could do each one separately. That's perfectly fine. We got to work backwards, though, whether we're working with this one or the 2 other ones. Can we find an antiderivative?
I'm going to say it's tangent.
Close.
Arctangent.
It's arctan. Okay. So this is a special one. I know it looks weird. But if you thought about your different techniques, there's no way you could do reverse power rule. U sub wouldn't work, because if you let U be the bottom, nothing would cancel out up top. We're not multiplying 2 different functions together, so by parts is out. And you can't factor the bottom, so partial fractions is out. Make sense? So it's either not possible, or it's a special one that we kind of need to recognize. So this is actually arctangent, and we're going to go from negative infinity to positive infinity. So if you were to think about the graph of arctangent, we want to figure out all of the area underneath this graph or curve, from all the way to the left to all the way to the right. Now if you thought about, and this is what's tricky, if you thought about actually plugging in infinity into arctangent, do we have any idea what those values would be? Probably not. Okay, so let's go ahead and maybe think about the graph of arctangent. Do we remember either the graph of regular tangent or arctangent? Uh-huh. It kind of looks like that S-curve. Okay. So, but this is like, yeah, like a DNA helix kind of thing. Okay, that's regular tangent. What would arctangent look like though?
It's like the side of this one, right?
It's the side one. Okay, so instead of looking like that, you guys and your dance moves. Yeah, we're looking like that. Okay, that does look familiar, right? Do we know where these asymptotes are? Can you think about a place on the unit circle where, let's see, if tangent is, that's a good guess, okay. If somehow tangent of x is 0 over 1, right, that means arctan would be 1 over 0, which is undefined. So where on the unit circle is tangent 0? Meaning the sine value is 0 and the cosine value is 1? I think I have that mixed up. No, I do. I'm sorry. Trying to think about how I want to phrase this. Let's see, this ordered pair is 1, 0. So the tangent value at that spot is 0 over 1, which is 0. This spot up here is 1, 0. So tangent would be 1 over 0, which is undefined. Okay? So if, sorry, I got it mixed up. If tangent's undefined at that spot, so is arctangent. What's this spot up here? Pi over 2. Okay? But you also could go negative pi over 2 if you traveled backwards on the unit circle. You would still have the same result. So we can fill in those asymptotes. So graphically speaking, okay, if you were to plug in infinity into this arctan graph, if you were to go off to the right forever, what value would you be approaching? Pi over 2. Okay. Then we have to subtract what we get when we plug in the bottom bound. If you were to plug in negative infinity, travel to the left on this graph forever, you would be approaching negative pi over 2. So it looks like subtracting a negative would change to a plus. So we're left with pi. All right. So a little tricky here because the integral it gives you, dealing with those two infinity bounds, you might not be able to physically plug them in and think about what value you're getting. But if you think about it in terms of a graph, that might help you out as well. Okay, just think about it as you go to the right or the left for those infinities. A little tricky with that one. All right, let's try another one that has these two infinities as the bounds. What do you guys feel like doing for B? Can we work backwards? Let's do detail by parts. Eric, if you want to do your tabular, that's fine. All right, what do you want to let dv be? What do you want to let u be? E to the negative x squared. So u would be x. What would you get if you worked backwards from v? Or backwards from dv? E to the negative x squared over x squared, is that what you said? Okay. Usually that's the pattern we use if this was like 4x or something like that, right? So this would be a negative 2x in the bottom. I don't know why this isn't erasing. I'm going to use a different color. Let me use a different marker. So we're saying e to the negative x squared over negative 2x, is that right? So you're telling me if we were to take the derivative of this, then we should get that, right? That's how we would check our work for antiderivatives. How would you want to find the derivative of this guy? It's a fraction, so quotient rule. Do you think if we went through quotient rule, it would simplify to that? No, because we know we're going to have a negative 2x squared left in the denominator, right? All right, so if we had e to like a 4x, a 5x, a negative 2x or something, that's fine, but the fact that it's squared is kind of throwing us off. So maybe by parts isn't the way to go. At first glance, it looks like it would be because you're multiplying two different things together. Let's do u sub. What do you want to let u be? It's a good recommendation. I mean, we only have so many techniques, right? Reverse power rule, u sub, by parts, or partial fractions. We can let u be the power. So if we rewrite it, we have x times e to the u, and then solving for dx to replace it, we'd have to divide the negative 2x over, and do the x's cancel? Hooray! Alright, so negative 1/2 coefficient, e to the u du, we should be able to work backwards from there. Isn't it just the same thing, basically? And then we can substitute the u back in. Alright, so we can approach this two different ways since we're working with infinities. We can either try to think about a graph like we did in the last one, or is there a way we can change this antiderivative into a fraction? That way we can compare growth rates. Do you have a preference? Try to draw a graph or turn it into a fraction? Yeah.
Can we just, the e to the negative x squared, like shift that to the bottom?
Yep. Negative power, you can move it to the bottom.
And then,
Alright, so if you were to plug in infinity, negative 1 over an exponential, which one's growing faster?
bottom?
The exponential. This is a constant. This is like the slowest growing function you'll ever have. So constant, basically constant over anything is going to be 0 because you're going to have the slowest over something faster. So that's going to approach 0, and then we have to subtract what we get when we plug in the other bound, which would be negative infinity. But what happens if you square a negative infinity? Infinity, so you have a constant over an exponential again. 0? 0 minus 0? 0. 1. Those are like the two results you guys always hate getting when you go through these problems, right? You hate getting 1 and you hate getting 0 because those are nice, easy answers from a difficult, complicated problem. What would we classify from yesterday these integrals as? Are they divergent integrals, convergent integrals? We're gonna transition into those, or that terminology, in the next unit a lot. How do you know? You have a finite area. Yep, you approach a value or you equal a value. So we're gonna say the integral converges. I know it wasn't part of the problem, but we're gonna get in the habit of that. Perfect. So even though, if you really think about it, even though you're analyzing the area from negative infinity to positive infinity, which is an infinite integral, you have a finite area. meaning as you keep adding up that area, it's getting so small that it's insignificant. Okay, it's not changing those values at all. Kind of interesting. Infinite interval finite area. Let's try calculator one. These are always the easier ones to do because you just type them in. Find the area of the region bounded by the graph and the x-axis. So let's get a picture of it first. Can we type that in? Is it dead? Yeah, you can go ahead and grab another one. Some of them, the batteries are dead. Some of them, the kids just turn off the, like the brightness or whatever, trying to play tricks. Is that one dead too?
Yeah, or it was turned down like a
I'll have to check it out. I know. Alright, so maybe they don't really give us any information in terms of a window. They just say bounded by the x-axis. So maybe we'll just start off generally with -10 to +10 in the window. Ooh, that's really tiny. We gotta go smaller. Alright, so my window is -10 to +10 on the x-axis, but then -1 to +1 on the y-axis. Bless you. Can we get that graph? Okay, so we'll just draw a little sketch of it in here. Kind of looks something like that. Alright, so it wants find the area of the region bounded by that graph and the x-axis. So all of this stuff. So it looks like the integral we're going to evaluate is an improper integral. We want all of the area from -infinity to +infinity. So we have an infinite interval, but maybe we have a finite area. We'll see if it converges or not. Alright, so let's see, we have 1 over the square root of 2 pi e to the negative x squared over 2. How do you want to type that in on your calculator? There's a few different things you could do.
I did the integral from -100 to 100.
Okay, so you use just a general, instead of like a -infinity to +infinity, you just use large values. Okay, so let's try that. We got 1. Alright, we'll make note of that. Is there any other way you want to try to type it in? Do you notice anything kind of interesting about the graph?
Symmetrical.
It's symmetrical. Okay, so Eric kind of mentioned something up here when we did the tangent one that may help us here. Maybe we can break it up. If it's symmetrical, maybe we can just find one section and then double it, because we know that the same amount of area is on the other side. So maybe we can try the area from negative 100 to 0, like where that symmetry axis is found. Do we need help typing in the function?
I think I both got 0.
Yeah, if you type in a bigger number, you get 0.
Do you really?
Yeah. It's just like that other thing.
Yeah, it was like the other one.
All right. Well, see how if we do negative 100 to 0, you get a half, and if you double it, you get 1. What were your bounds? Negative. Did you do 1,000 or 1,000,000 or something?
-100, no, -10 million.
I put 7 zeros.
7 zeros. 1, 2, 3, 4.
Infinity.
This might be like the other one. I have no idea why the calculator does that. Because I think I told you guys I wasn't able to figure it out,
Yeah.
right?
It's basically like the other one, because like we plugged in a smaller number in it.
Right. Wow. Hopefully, we know that's incorrect, right? Because there is area under the curve, right? Why is it saying... Huh. Let's try this. Do you guys know you can highlight the area under the curve on these graphs? Do you know how to do that? Okay, so let's say if you were to graph it, check this out. If you go to second trace, like where the max, min, intercept, all that are, you see how 7 is an integral, right? If you hit that one, it's asking you for a lower limit. So maybe we'll use Eric's negative 100. Oh wait, it has to be within your window that you use. So the lower limit we'd be able to use is 5, I guess. We'll do lower limit negative 5, upper limit 0. Notice how it'll shade that. And it's 0.499999. So using symmetry, we would have the other side. I have no idea why it's getting 0. Let's try that for a second. You did 7 zeros, right?
Yeah.
What if we use that as the x min and x max? It's going to look really tiny, though. Like you can barely even see the function. It still gives you 0. Craziness. Okay. I'll have to look.
So if you change the bounds to the bigger number,
Yeah,
you get 0.
you get 0. But we know that's not true, right? Because
It's still the same graph, it's just the windows.
the window's different, exactly. That's
Conspiracy.
well, okay. So this actually happened. Hold on. This actually happened in the AP class the other day. I wonder if I can get out the example. This is why a calculator is useful, but you're not supposed to let it replace your brain. Okay. Check this out. Remember how last year we were talking about like sharp points and differentiability, vertical tangents, all that fun stuff? So one of their questions was f of x equals x to the 2/3 plus 2. No, wait. Wrong one. Bless you.
I think
You don't have to write this down. But this, I'm going to show you an example of why a calculator is just crazy and you need to trust yourself more than it most of the time, okay? If you were to take the derivative of that, we'd have 1/3 x to the negative 2/3, and we can bring that back down to the bottom and make it positive, right? If you plugged in 0 for the derivative, what would you get? 1/0, which is undefined, right? So graphically speaking, if a derivative doesn't exist, we know it's a sharp point, vertical slope, endpoint, something like that, right? If you were to use your calculator, okay, so math 8, you know how you can type in derivatives on your calculator? If you type in x to the 1/3 power plus 2, and you want to plug in 0, it gives you 100. Shouldn't it be undefined?
How would you?
Right? I have no idea how the calculator got 100 yesterday. That was interesting. I wasn't really anticipating that. Now, if you think about it, if this is a derivative, this is representing a slope, and if you were to go up 100 units and over 1 unit, isn't that technically fairly steep? So this is signifying a vertical tangent at 0. Okay, but realistically, it should be undefined. Why the calculator gives you 100, I have no idea. So we can use the calculator, but not necessarily trust it all the time. Moral of the story. All right, so I like Eric's 1 better than the 0, because if you were to take a look at the graph, clearly we know there's some area under there. Okay, the 0 is just not making too much sense. Okay. All right. Do you know what? I know we still have about 10 minutes left, but this is too important for us to end in the middle of, so we're going to just save it for tomorrow. Okay?